Okay, the first part of this, looking through the application for assignment 4, is to actually look at the SIG test, the command line version of this, and take a look at that. First, we're going to generate some keys, then we're going to do some validation with some keys. And that is, if you are in the directory for the assignment, do a git pull. I did add some code to this assignment today, and inside SIG test. Okay, let's take a look at the command line. We have this SIG test. And it's a tool for dealing with signatures. These key files and these signatures match with what you see in Ethereum. So this allows you to, at the command line, interact with these signatures. You've noticed that I've got some key files out here. They have passwords. But we're going to go poke into them with stuff. So you can use this tool. So if I just generate a signature with a random password, I end up with a new signature file over here with this name. And it has an address that gets created. That address is 24 out of 32 bytes of the public key of the public-private key. And here is the random password that gets generated that matches with it. So that's what it takes to generate a new account, is we just create one of these things, and we hope that we don't have a collision. Of course, this is 2 to the 256, and consequently, it's a big enough space that the likelihood of collisions is negligible. Also, a collision doesn't say that you have the same private key. It says only that you'd have a collision on the public key. So you wouldn't, even if there was a collision, you wouldn't be able to spend somebody else's money. It's just that your key wouldn't work for accessing that account. Now, okay, inside SIG test, when we want to verify some messages, if you look at the make file, there's some examples here. And most importantly, if you look at sign 2 here, you'll notice that it has the password echoed out so that I can actually type that in. I'm not good at typing that password. You can run this way, just running that command, but it's long enough with all of this stuff out here that I'm not going to type that in either. So let's just cut and paste that password, and we generate a signature. Now, it tells you that the message length is 34. Okay, there's the message in hex from the original message. I don't remember what the message was. Some data to sign. It's quoted there on the screen. And there is the signature, which should be 65 232s, and it is in sector 1, or quadrant 1 of the graph. So there is a signature and a signed copy. That's what you should expect for values. Now, since this is randomly generated, that signature will change every time. I'd expect the message not to change every time. It will be the same. So down here a little bit lower, we have a verify, where we've gotten a message, okay, and it's got a signature, and it's going to verify that message. So let's try the verify and see how it works. Now, verify 1. And it says that on verify 1, the signature does not match, okay? And I think that's actually the correct result. I've gone in somewhere and altered the signature so that you can check the case of a bad signature. And if we do verify 2, okay, it's a slightly different value for the signature, and it says that the signature verified. And it returns to us the public key and the address of that signature. So these are the kinds of things that we're looking for. Now, of course, since this is all in here, if you look at the code that you're interested in is let's see, okay? If you look at the Go code, there is a sign message, which I bet has the code in it for doing the signature, and there's a verify message that has the code in it for doing a verify. We'll come back to those, but chances are that if we go poking into those, since that is the source code for what we're trying to do is sign and verify messages, we're going to see how it's done. All right, we'll be back to that later.